Hi everyone, my name is Giovanni Geraci. Welcome back. This is class number 5 of the course Signals and Systems 2 at Universitat Pompeu Fabra in Barcelona. If you have any questions on this class or any of the previous ones, feel free to get in touch via email. You can also check my webpage for more information about me and the course. In the last two classes, we first learned how to represent periodic signals with a Fourier series, which is a linear combination of complex exponentials, and then how to determine the coefficients of the series. Later on, we learned how to deal with signals that are not periodic by introducing the Fourier transform, which is an integral rather than a series. Today, we will learn how to calculate the Fourier transform of periodic signals. So let's get started. In the case of periodic signals, we won't be able to use the Fourier transform formulas we derived in the last class. That's because the Fourier transform integral only converges for finite energy signals, and periodic signals have infinite energy. So we will have to find another way. So let's recall the Fourier transform pair. X of t, a signal in the time domain, can be expressed as a linear combination of complex exponentials through the relationship x of t equal 1 over 2 pi, the integral of x of j omega, which is the Fourier transform, e j omega t d omega. And how to determine the Fourier transform? It's a similar formula. So x of j omega is the integral of x of t e minus j omega t dt. So the Fourier transform, once again, is a representation of a signal x of t as a linear combination of complex exponentials at different frequencies. We already said that the Fourier transform converges if x of t has finite energy, which means that the integral of the square magnitude of x of t is finite. And this does not hold for periodic signals. So when we treat periodic signals and we want to determine the Fourier transform, we will have to use a different method. This is what we will learn today. We can actually obtain the Fourier transform of periodic signals by using impulses. So to begin with, let's note that for x of j omega equal 2 pi delta of omega minus omega 0, meaning an impulse centered at the frequency omega 0 with amplitude 2 pi, the anti-transform x of t can be very easily obtained. So let's just use the formula for the anti-transform. We get 1 over 2 pi, the integral of 2 pi delta of omega minus omega 0 times the usual complex exponential ej omega t d omega. Evaluating this integral is very easy. It's very easy if we recall the property shown at the bottom of this slide. So when we multiply an impulse by a certain signal, what we obtain is the same impulse scaled by the value of the signal where the impulse is centered. So we've seen already this in the time domain, but it's perfectly analogous in the frequency domain. So see the example, the delta of omega minus omega 0 x of j omega, where x is a general signal in the frequency domain, equals delta of omega minus omega 0 x in j omega 0, right? So if we just apply this to the integral, we see that the result is very simply e j omega 0 t. Right, let's make this more general. More in general, if instead of a single impulse centered at omega 0, we have a linear combination of several impulses centered at frequencies k omega 0, integer multiples of omega 0, with different coefficients ak, well, we simply get that the anti-transform of such thing is x of t equal the sum of ak j omega 0 t, right? So this is because we just showed that one impulse has as an anti-transform a complex exponential, so a linear combination of such impulses has as an anti-transform a linear combination of such complex exponentials. But the funny thing here is that this is just exactly the Fourier series representation that we have learned about, right? So in summary, we can see that the Fourier transform of a periodic signal with Fourier series coefficients ak, as the one you see at the bottom of the slide, can be interpreted as a train of impulses, like the one represented just above, occurring at the harmonically related frequencies, so at frequencies k omega 0, and for which the area of the impulse at the kth harmonic frequency, k omega 0, is 2 pi times the kth Fourier series coefficient ak. It's a very interesting relationship. Let's clarify it in the following slide once and for all. So we have that given a periodic signal x of t with a Fourier series representation that we see in this slide, the classical one, its Fourier transform is the train of impulses x of j omega equal the sum of 2 pi ak delta of omega minus k omega 0. So it's a train of impulses where the impulses are centered at frequencies k omega 0 and they have amplitudes 2 pi ak. Let's see some examples to put into practice what we just learned today. The first example we'll see is the periodic square wave. Again, it's a very useful signal. So it's defined as 1 in a certain interval, so between minus t1 and t1, for example, and 0 elsewhere in the period. And then this is replicated with a certain period t, as you can see in the figure. For this signal, we know what the Fourier series coefficients are. We have derived them together in a previous class, but let's just repeat it here for simplicity. AK is, by applying the formula, 1 over t, the integral over one period of the signal, which is 1, e minus jk omega 0 t. This integral can be easily calculated and written as a sine of k omega 0 t1 over k pi. Cool. Now that we know what the Fourier series coefficients are, based on what we learned in the previous slides today, we can write the Fourier transform in terms of impulses. Let's do that. So the Fourier transform x of j omega, as we learned, is going to be an impulse train where the impulses are centered at frequencies k omega 0, being omega 0 the fundamental frequency of our periodic signal x of t, with amplitude 2 pi ak, being ak the Fourier series coefficients, right? So for this particular case of the periodic square wave, we have the sum of 2 sine k omega 0 t1 over k delta omega minus k omega 0. And what does this look like? We have a figure at the bottom right of this slide that shows the trend of these impulses. Their envelope follows a sinc function because the coefficients ak of the Fourier series have a sinc behavior. It's the sine of k multiplied by something divided by k multiplied by something, right? And they are centered at frequencies 0, omega 0, 2 omega 0, 3 omega 0, etc., minus omega 0, minus 2 omega 0, and so on and so forth. Let's now see another example, which is the sine wave. It's a very simple one, but it could be very useful. So if our signal x of t is the sine of omega 0 t, we know we can write this as a difference of complex exponentials, such as e j omega 0 t minus e minus j omega 0 t over 2j, right? And from that, we know that we can, just by simple inspection, obtain the only two non-zero Fourier series coefficients, a1 and a minus 1, which are 1 over 2j and negative 1 over 2j. All the other coefficients are 0. So we already know this from previous classes, but today we're able to write the Fourier transform of the signal x of t based on this information. So x of j omega is going to be, again, a train of impulses. The impulses will be centered at frequencies k omega 0 and will have amplitude 2 pi ak. Since in this case only two coefficients are non-zero, there will be only two impulses centered at omega 0 and minus omega 0. And their amplitudes will be 2 pi ak, which is equal to pi over j and minus pi over j. We see this represented on the top right of the slide. A very similar yet different case is the one of a cosine signal. So in this case, we represent the cosine of omega 0 t as a sum of exponentials, as you see at the top of the slide. And we already know that the Fourier coefficients are 1 over 2 for a1 and a minus 1, and all the other coefficients are 0. So following the same procedure, we obtain the Fourier transform x of j omega as a train of impulses, again where there are only two non-zero impulses. The amplitude is pi for both of them, and they're centered at omega 0 and minus omega 0, as you see in the figure on the top right. One more interesting example for today is the one of the impulse train. This signal is extremely useful, and we will make use of it when we will explain the concept of sampling, right? So the impulse train is defined as a sum of impulses. They are equally spaced. In our example, their period is t, so they are centered at times kt. So 0, t, 2t, etc., minus t, minus 2t, etc. And for this signal, we have calculated previously the Fourier series coefficients, ak, and we have seen that all of them are equal to 1 over t. How did we obtain that result? Well, very simply by solving the integral that you see at the top. Then, by knowing this, again, and by putting into practice what we learned, we can write the Fourier transform of the impulse train, and we know that it's going to be a train of impulses in the frequency as well. What we need to determine is the position of these impulses, and that's easy because they'll be centered on multiples of the fundamental frequency omega 0, and omega 0 is going to be 2 pi over t. And we need to determine their amplitude. Their amplitude is 2 pi ak, and in this case their amplitude is the same for all of them because it's going to be 2 pi over t. So we can write in formulas that x of j omega is 2 pi over t, the sum of delta of omega minus 2 pi k over t. So thus we have seen that the Fourier transform of a periodic impulse train in the time domain with period t is a periodic impulse train in the frequency domain with period 2 pi over t. This is sketched in the slide we're seeing now. So here again, we see an illustration of the inverse relationship between the time and the frequency domains. So as the spacing between the impulses in the time domain gets longer, meaning that t gets larger, correspondingly the spacing between the impulses in the frequency domain gets smaller because 2 pi over t becomes smaller because omega 0 becomes smaller. So a larger spacing in time corresponds to a smaller spacing in frequency and vice versa. So that's all for this class. By now, we know how to calculate the Fourier transform for both periodic signals and non-periodic signals. In the next class, we will learn some basic properties of the Fourier transform, and knowing these properties will be very useful to understand the relationship between time and frequency representations of signals. Also to help reduce the complexity in evaluating the Fourier transform in many cases. See you in the next class.